Good day everyone, my name is Carlton Chen and I am from Group 2, and for our open-ended design project titled is Design and Implementations of a magnet-based QPSK digital test communication system over an NWGN channels. Okay, our main objective was to bridge theory and practice by building a full end-to-end communication link, covering everything from signal generations and modulations through a noisy channel to demodulations and error analysis. We choose QPSK because it encodes 2 bits per symbols onto one of 4 carrier spaces, and this gives us twice the spectral efficiency of BBSK within the same bandwidth, which is exactly why QPSK is widely used in 4G, 5G, and optical systems. Furthermore, we implemented gray coding so that neighboring phase state differ by only a single bit. This effectively minimizes bit errors when noise pushes a symbol across a decision boundary. And here is our overall system architecture on the transmitted side. The input test is first converted into a 8-bit binary string, grouped into 9 bits, and mapped into gray code QPSK symbol. And these symbols then pass through the channels where complex NWGN is injected. Finally, the receiver side we utilize minimum Euclidean distance detections to decide which symbol was sent, convert those symbols back to bits, decoders into EXITs, and successfully recover the original test message. We implemented this entire link in pure MATLAB without relying on communications to both bots. Divided into 6 key stages. First, we encoded the target test QPSK lat4 into binary, and second, we modulate this bit into QPSK symbol using gray mappings, and third, we inject Gaussian noise at our target EB over NO, and fourth, we demodulate the received signal using minimum Euclidean distance, and fifth, we reconstruct the test, and finally we spread the EB over NO from 0 to 12 dB to compare our simulated result against the theoretical big error rate. And this slide shows our constellation strength at 8 dB. The four blue dots represent the ideal noise-free QPSK symbols located in each quadrant at plus minus 0.707, and the red dots represents the actual received symbol after passing through the noisy channels. So as you can see, the received symbols from tight clusters around each ideal point and stay well within their respective quadrants. Since no symbol crossed the decision's boundary, every single symbol was decoded with 100% accuracy. Notice that these clusters are perfectly circular. This is because NWGNs add equal independence noise to both in phase and quadrants axes, resulting in a radially symmetric spread. Now let's look at our big error rate curve. The solid blue line represents the theoretical QPSK performance, while the red dashed line shows our simulation result. From 0 to 6 dB, you can see that our simulation tracked the theoretical curve almost perfectly. Beyond the 6 dB, however, the simulated line seems to stop, but this is actually expected behavior, not a bug. Our test message QPSK lat4 is relatively short, So only 376 bits. Statistically, at 8 dB, you will need around 5263 bits before a single bit error occurs. Therefore, in our simulations, we achieve zero errors since the logarithm of zero cannot be plotted on a log scale. The curve simply breaks, and this gap actually confirms that the channel quality at this point is exceptionally high. To summarize, we have three key takeaways from this project. First, AWGN is isotropic. It perturbs the I and Q channel equally, creating those symmetric circular noise clouds we observe. And second, our simulation perfectly match the theoretical curve whenever errors occur, which fully validates our graph mappings and decision logic. Thus, the message QPSK led for was recovered with zero error at 8 dB, demonstrating a fully functional, reliable end-to-end link under moderate noise conditions. So in conclusion, our MATLAB-based QPSK communication system successfully demonstrate the entire digital communication pipeline. And this project has successfully fulfilled all requirements of our open-ended design. So I think that's all for me. Thank you for your time.